To solve Leetcode problem 1591, string splitter 2. And let's first try to understand the problem. So we are giving a string splitter with the following two special requirements. So on each tier, the splitter will print a solid rectangular pattern of a single color or grid. So for example, for the first tier, let me make it better. Yeah. So for the first tier, this is our grid. It is empty. So for the first tier, we're gonna print all the grid with color 1, so it is like this. And for the second turn, we're gonna use color 2 to cover these areas. So this is our target grid, so it is this one. And we just want to check if we can realize this kind of printing. So as you can see, at the surrounding areas it is 1, but in the middle it is 2. So this is okay. Yeah. So this is the description. So once the splitter has used a color for the above operation, the same color cannot be used. So this is for first operation we use the color 1, and for the second operation we cannot use the color 1. We have to use another color, maybe 2, 3, or others. It is okay. So we are giving this kind of a matrix m times n with target grid, and the value is just the color, and the position is the row and column. So we're going to return true if it is possible to print the matrix of target grid, otherwise we're going to return false. So let's try to analyze some situations. First of all, let's try to analyze this one. Yeah. So from the beginning, all the areas, the surrounding areas, are going to be 1, but inside, in the middle, inside of the smaller grid, all the areas are going to be 2. Yeah. So this is 1, this is 2, but what is inside these areas is going to be 1. Is this possible? As you can see, this is 1, 1, 1, always to be 1. But for this grid, it's going to always be 2. Always be 2. But inside, it's going to be 1. Is that possible? Yeah, you can imagine. First of all, the first step, we're going to print these areas. Yeah, so this is the first step. It means all areas are going to be 1. Now, we're going to use 2 to cover. So if we use 2 in these areas, basically, we're going to use 2 to cover. Yeah, but for here, if we want to print these areas, basically we need to use another color. We cannot use 1 anymore. So this means this is not possible. Yeah. So this is one case for analyzing the problem. It means there is some structure about the sequence of the printing. So first of all, we can use some kind of sequence. We're going to use print 1 first and print 2. Yeah, this is okay. But after 2, we have to print 1. So this means there is a loop. So if there's a loop, there's a circle for this kind of a structure. It means it is not possible. So if this is possible, it must be another number, maybe 3. So it means 1, 2, 2, 1, 2, 2, 2, 3. And only this is possible. So this is how we're going to analyze the problem. Yeah. And the second way is that we cannot analyze the whole areas as the topological structure. We cannot analyze this is 1 and this is 2, the whole areas as the topological structure, because it will have the mistakes. So for example, we can try to use this example. Yeah. So here is 1, 1, 1, okay, and here is also a 1, but here we're going to have 2. So is this possible? Is this true or false? So first of all, in the first step, we're gonna cover all areas with 1. This is okay. And now we want to cover these areas with 2. So this is 2, this is 2, but here should also be 2. Now it seems it is not possible if we want to print it like that. Yeah. So this is not possible. This means while we are analyzing the problem, we cannot build the topological structure using the whole area. This is the area, this is another area, then we build the topological structure. We cannot use it like that because you can see this kind of testing case. It is not possible. So, but how can we build the topological structure? So we're going to use, first of all, we're going to choose an area. First of all, we're going to choose an area. For example, this area is 1. Yeah. But for the second loop, we're going to check only a single node, only a single point we want to check if it is inside this area. So for example, this area is 1, we want to check if there's a single number, for example, if there is a 2 inside it. If there's a number 2, another color inside it, it means we can build the topological structure. It is 1 to 2. Yeah. Even there are any other 2s, it doesn't matter. We just need to find 1. Because if we find 1, definitely there's a topological structure of 1 to 2. Yeah. Now we want to build another structure. So for example, this area is 2. Okay. And inside maybe there is a 1. Yeah. So we want to check this area is 2. If we can find a single dot, that is 1. So for example, this is 1, a single dot. This is 1. If this is a color 1, definitely we have a topological structure. It means we're gonna cover 2 first, and then we're gonna go to 1. This means this is not possible because there's a loop for the topological structure. But for the topological structure, it should be a DAG, directed acyclic graph. Yeah. But if this is 3, so this is okay. We can build the topological structure like 1, 2, 3. Yeah. So if we can always build the topological structure, it means we can return a true. It means we can print it. Otherwise, we're gonna return a false. Yeah. So if you understand the idea of how to solve the problem, now we can just use topological sort to solve it. Although there's gonna be a lot of coding, but I think the idea is very important for us to understand the problem. Normally, if you understand this idea, yeah, basically you can solve the similar problem, the similar grid problems, because a lot of grid problems we need to use the topological idea to solve it. Yeah, so definitely this is going to be a hard problem. Now we try to solve it. So I'm going to use R and C as the length of the target grid as the row and column. Yeah, so it's going to be length of the target grid with 0. Now I want to put all the colors inside a dictionary, so I'm going to prepare a color dictionary. It's going to be a default dict. Inside is going to be list, and I want to put all the colors inside. So for R in range capital R, and for C in range with capital C, and we want to put it inside the color dictionary. It's going to be the target grid with RC gonna append. We want to put it as a list, so it's going to be the row and column. Yeah. So from this color dictionary, basically for any color, for example, this color is 1, we're going to find all the positions. And this is important for us to find the areas of the grid, because this position, we're going to use this position to find an area. Yeah, and we can also use this position to find any dot. So this color is really important for building the topological structure. Now we're going to build it. So for the topological sort, we're going to prepare G and integrate. The G is going to be the graph and default dict. It is also the list. And for the integrate, I'm going to prepare it as the color with 0. So from the beginning, the integrate is going to be 0 for any color. So for C0, for C in color. Yeah, inside that color dictionary. Now we are going to build it. So for color 1, inside the color. So first of all, we're going to find a big area. And for this color 1, we're going to find a big area. So this is going to be the x-axis. So it's going to be x1 and x2. Basically, this means the big area. So from here, this is x1 and this is x2. Okay, and this is y2, and here is y1. Basically, we need to find this kind of area. So x1 and x2 gonna be the we're gonna use the minimum of item 0. So for this item inside the color with the C1. Basically, inside of the C1 it's gonna be an array, but we want to choose the minimum value for this x1, and the position gonna be this item 0. Yeah, and similarly, we're gonna prepare a maximum. So in this way, we're gonna find the x position, x coordinates for x1 and x2 for the area. So here we're gonna change it to max. Yeah. Similarly, we're gonna prepare y2, y1, and y2. this is for finding the y-axis, top axis and bottom axis. So we're gonna use the minimum of item 1, and here gonna be the maximum of item 1. So in this way, we're gonna find the area. Yeah. If we find this kind of area, the next step is we want to check any dot, if it is inside the area or not. If it is inside, we're gonna build the topological sort. If we find one, we're gonna break it immediately because we don't need to duplicate all the dots. We just need to find one to build the topological structure. Now we are going to check another color, C2. So C2 inside the color. We need to check it must be a different color. So C1 not equal to C2. So we're gonna check all the coordinates. So for x, y inside the color C2. And we want to check the structure. If x1 less than equal to x less than equal to x2, we just want to check if it is inside or not. So if it is inside, and this is going to be y2. If it is inside, definitely we're going to build this kind of topological structure. So it's going to be the big one first. So the area going to be first. C1 need to append C2. Then we're going to append this dot. Because we're going to first print the big area, then we're going to print this smaller area. But this dot can represent the smaller area. And similarly for the integrate, it's going to be a smaller area, C2 plus equal to 1. But we need to break it immediately because we just need to build one kind of this structure. If it has the same color, it is okay. I mean, it has the same color, it is quite okay, but we need to break it immediately. Otherwise, we're going to have the duplicate integrates. It's going to be totally wrong because we just need to build a data topological structure. Just use one dot is enough. Yeah, even there is a similar dot inside, we don't need to build it. Yeah, otherwise the integrate will be integrates. It is just a duplicate. We don't need to do that. Now, if we build the topological structure, we just need to finish the BFS part. So I'm going to prepare a queue and a counter. So the queue is going to be the queue, and inside is going to be I for IV in integrate.items because currently it is a dictionary, and this way should be 0, and the counter is going to be 0 as well. And then we're going to check this queue, and we're going to pop it as a node, q.pop left, and we're going to check the neighbor in this graph. So for neighbor in graph with this node, we're going to check the integrate with this neighbor should minus equal to 1. So if we integrate with this neighbor equal to 0, basically this means we need to put the neighbor this color inside the queue. Finally, we just need to check if this count equal to the length of the color, how many colors and how many count. If there's the count equal to the color, definitely it's going to be true. Otherwise, it's going to be false. So whenever we pop out a node, so the counter gonna plus equal to 1. Yeah. So this is the whole structure of this problem, and this is the entire coding. And the difficult part, I think, it is only about these areas. Yeah. It is a single dot inside an area. If it is possible, we're gonna build the topological sort structure in these areas. Yeah, this is 3 lines gonna these 4 lines are gonna be the hard part of the problem. Yeah, so we're gonna break it immediately. Yeah, I mean I think except that the problem gonna be except those 4 lines of code, or other lines of code should be really easy to understand. Yeah, so definitely you need to understand this kind of area because this areas basically is used to build the topological structure. Now let me just run it first to check. It seems that it is okay. Now let me submit it to check if it can pass. Yeah, as you can see, it passed, and it is I think it is really fast. As you can see, it is just 0.1 seconds. Yeah, I think it's really fast. This is because let's just analyze the time complexity. To analyze why it is so fast. So for the topological sort structure for here, because there are only 60 colors, and basically we're going to use the colors to build the graph. So in these areas, the time complexity going to be E plus V. number of edges plus the number of vertices, but the vertices is going to be 60. It is the color, and the edges maximum is going to be 60 square. Yeah, so for here, it's going to be n square. N is the number of colors. It is okay. Yeah. Now let's analyze this area. So in this area, this is just m times n. It is also the same, 6 times. Yeah, let me check. This is yeah, it's also the same because mn is 60. It is also 60 times 60. This is also n square. Yes. Now let's analyze these areas. This is a color 60, and this is another color with 60, n times n. Yeah, because basically for here, we are checking the color array. Yeah, so for this array, for each of the items, how many items inside a color? Yeah, this is dependent on how we're gonna build the testing cases. Maybe for here we're gonna use yeah, because for here tag definitely it can be 60 or it can be 60 times 60. Yeah, but our average we're gonna use it as 60, so it is the same as here. I think 60 times 60, and here definitely we're gonna have another 60. So I think the time complexity gonna be 60 cubic. Yeah, maybe you think for this areas maybe we're gonna use another 60. Yeah, actually it is not, and because for average while we are building the structure and we're gonna break it immediately. Here is here if we find one, and we're gonna break it immediately. So for each of the part, we just need to use this kind of 60 cubic gonna be the time complexity. That is why it is so fast. Thank you for watching. See you next time.